Skateboarding, like a lot of things, is about energy. So what we're seeing here is a video of somebody skateboarding. Let's take a look. Down the ramp, up the ramp, down the ramp. If you notice, the skateboarder is using gravity to his advantage. He lets himself fall. Now, every time you climb up on something, you're giving yourself more and more potential energy. You have more and more potential to fall. The higher you climb, the more potential you have to fall. This is called gravitational potential energy. Once you let yourself fall, like the skateboarder here, and you get down to the bottom of the ramp, well, you've fallen as far as you can. What happened to all of that gravitational potential energy? Well, it's not gone. It's just now changed forms. You might be saying to yourself, well, he's moving now. And if he's moving, he's got kinetic energy. So a skateboarder uses gravity to fall, gracefully of course, up and down the ramp. So gravitational, now back to gravitational, to kinetic, to gravitational, and so on and so forth. What happens when said skateboarder falls? Well, let me find a good fall here. So, potential, kinetic, back to potential, back to kinetic, and to kinetic, and boom!
Oh my God.
Thermal energy. So we're going to be looking in a second here at a more specific example with some charts and graphs. So here we're going to look at a FET simulation with the skateboarder in the skate park. So what you'll notice is I've drawn a line at the bottom here, and it represents where the potential energy is 0. So if I take the skater down to this line, that will be his base height level. That's going to be where the potential energy is 0. So as I said before, anytime you climb up above that, you're going to be giving yourself potential energy, the potential to fall. So we're watching him fall back and forth and back and forth. The question is, what does that look like if we just look at the energy? The energy associated with that movement and that transformation of energy. Turns out, when we pull a bar graph in, we get this idea here. So what we'll notice is, over on the bar graph, we've got kinetic, potential, thermal, and then the total mechanical energy. So as the skater moves back and forth, you're probably noticing that the total energy doesn't change. All that's happening is, it's going from potential to kinetic. When we're at the bottom, the potential energy is very low and the kinetic energy is very high, because the skater is going to be moving its fastest at the lowest point. As we get to the top, we notice all potential, no kinetic. For the same reason, the skater slows down and stops. If you're not moving, you don't have any kinetic energy. So stops just for a second and then begins to move back down. Wonder what this looks like in a pie chart. So what we're seeing here again, same situation, just in a different graphic. The blue represents potential where the green represents kinetic. Down toward the bottom, mostly kinetic. Back to the top, mostly potential. Now this is a perfect situation. We're not dealing with any friction. So if I go over here and I add some friction, I'll bring my bar graph back in so we can watch that too. Add a little bit of friction and then see what happens. So what you're seeing is that energy now is turning into thermal, which we talked about is a type of energy that we haven't found a good way to harness, to use. So once we get thermal energy out there, or use the word entropy, you're adding entropy to the system, we can't find a good way to bring that back in and use it again for other types of energy, or transform it into a different type of energy. So let's clear this. I'm going to take the friction back off, and I'm going to look at another graph. So we're going to eliminate this one. No pie chart. I'm going to bring in this graph. Clear it. Bring it up here. Have them ready to launch. And now this is going to show us energy versus position. So position on the bottom and energy on the side. So right here represents the dotted line. We're going to be looking at the types of energy that it has right there. Total energy in yellow, not changed. Green represents kinetic. It's going to be very high here. The potential is going to be very low, and we don't have any thermal. So that's at the bottom. As you move toward the top, so kind of midway through, if we bring it back, let me play this out. Whoops. Sorry about that. Let me. There we go. So we'll get that graph back. So we'll stop it again at the top. So this is that top graph. All potential, no kinetic. At the bottom, this is the graph. Now somewhere in the middle, we're looking at combination of both types of energy. But remember, the total mechanical energy is always going to be these two added together. If we're up here, we have very little potential, and vice versa. So let's look at that one more time. So we watch the energy convert back and forth. We add our bar graph. We see it moving back and forth from potential to kinetic, but the total stays the same. And if we look at the energy versus the position, we get that same idea. Pause there. All potential. All potential. Pause there. Mostly all kinetic and mostly all kinetic. We add some friction in and watch it all go. Okay, we're left with just thermal energy. So thanks for listening, and we'll see you next time.